Have you ever wondered how powerful artificial intelligence models, especially those dealing with language, manage to understand long, complex sentences or even entire paragraphs, and then generate coherent responses? It feels a bit like magic when they process a vast amount of information and distill it down to its core essence. At its heart, a context vector conveys a dense, fixed-size numerical representation that encapsulates the essential meaning and relevant features of an entire input sequence. This allows neural networks to effectively carry forward a comprehensive understanding from one part of a task to another, serving as a critical bridge of information. The core mechanism behind this lies within an encoder-decoder architecture, particularly prominent in sequence-to-sequence models. The encoder component processes the input data, like a source sentence in machine translation, word by word. As it processes each element, it builds an internal understanding. This understanding is then compressed into that single context vector, which effectively becomes a summary of everything the encoder has seen. This vector is not just a collection of keywords. It contains rich semantic meaning, syntactic relationships between words, and even the nuances of the original input's intent or emotional tone, all depending on how the model was trained. It is an abstract, distilled representation of the input state. Understanding the concept of a context vector is fundamental for grasping how advanced neural networks perform complex sequence-to-sequence tasks, such as neural machine translation, text summarization, and sophisticated question-answering systems. It illustrates the remarkable capacity of these models to abstract, compress, and retain critical information across various processing stages. Recognizing its role also provides insight into why models might struggle with very long sequences, as compressing immense amounts of information into a single fixed-size vector can sometimes lead to an information bottleneck, a challenge attention mechanisms later helped address. Before the widespread adoption of full attention mechanisms, this single context vector was often the sole source of information passed from the encoder to the decoder. This bottleneck was a significant limitation, especially for very long input sequences where a fixed-size vector struggled to retain all necessary details. The advent of attention mechanisms evolved this idea, allowing the decoder to selectively look back at different parts of the encoder's output, essentially creating a dynamic context vector for each output step, rather than relying on one static summary. Ultimately, the context vector serves as the condensed memory of the input, enabling models to perform tasks that requiring deep comprehension and the generation of entirely new, contextually relevant outputs. By summarizing the what and how of the input, it allows the model to bridge the gap between understanding and generation, providing the essential foundation for subsequent processing and output creation, thereby transforming raw data into meaningful actions or coherent text.